So in today's lesson now I will be talking about the velocity time graph. So when we talk of the velocity time graph, we will be checking on, or we'll be exploring on how the velocity of an object changes over time during its motion. And the other thing that we have to know is the relationship between velocity and time. So the relationship between the two quantities is that the velocity is directly proportional to the time. And we also learned that when we were doing equations of motion in grade 10, when we were doing motion in one dimension in grade 10, we were told that the velocity is directly proportional to the time. So this statement will only be true if and only if we have a constant acceleration. So if we have a constant acceleration, then the velocity will be directly proportional to the time. What do we mean by directly proportional? So we mean that when we increase the velocity, the time will also increase. Or when we decrease this quantity here, this one will also decrease. So when we represent this on a graph, we're going to have the time on the x-axis, since it is independent, and we have the velocity here. Then the relationship between the two forms a straight line, which shows the relationship between or the proportion, the direct proportion between the two quantities. Then when we see a straight line in maths, we know that we can represent a straight line function using y is equals to mx plus c. The reason I'm bringing in this, it's because I want to show you something and the equation that best describes the relationship between the velocity and the time, and which shows us the direct proportion. We know that the gradient is constant. So suppose we're having point O here, which is the origin. Then we have point A, point B, point C here. We know that when we want to find the gradient of AO or of AB or of BC, the gradient will be the same, because these points are collinear points. For as long as the points lie on this line, the gradient will be constant. So we can see that from this equation of a straight line, the constant variable here, it's our gradient. Then when we bring in the formula which was derived from the to form the equations of motion in this vertical projectile motion, we can bring in this formula: Vf is equals to V initial plus the gravitational acceleration multiplied by the change in time. So this formula best describes the relationship between velocity and time, and it will show you the proportion, or the direct proportion relationship. So if you can see, when we talk of vertical projectile, that is where if we're having an object here, and this object, the only force acting on it will be the gravitational force. And we know that this gravitational force is the gravitational acceleration, which is 9.8 meters per second squared. We know that this gravitational acceleration is constant when we deal with vertical projectile motion. So now you can see that this quantity here, or our g, it's the constant acceleration that we're talking about. Hence now the velocity is directly proportional to the time. All right, so now if we redraw, or when we draw in maths, we have the x and the y axis here, and then this is a straight line graph. So we have the constant multiplied by whatever it's in the x axis. Then when we look at it in physics, we have the constant, which is the gravitational acceleration, multiplied by whatever it's in the x-axis, which is time, in this case, the quantity of time. So you can see that this part here, it's similar to this part here. Then we have the c, or the constant, or we can call it the vertical shift or the y-intercept. So if the value of c is 0, then the graph will start from the origin. But if c is positive 2, then the graph will start at point 2 moving upward. So this can be called the vertical shifting or the y-intercept. Similarly, when we look at the initial velocity, this is the velocity, or this v initial determines where the graph should start. For an example, if your initial velocity was 5, then it was going to start at 5 moving in a certain direction. So this v initial tells you where the graph really starts. So if we rewrite this, vf is equals to g multiplied by change in t plus v initial, then this it's similar to y is equals to mx plus c, because we have a constant, this is a constant, whatever it's independent, then this is the independent variable, and then we have a constant, or the vertical shifting. So the two determines a straight line, and by straight line we know that these two quantities, they are directly proportional. Why? Because we have a constant acceleration here, which is 9.8 meters per second. So in maths, we know that we have a positive gradient and a negative gradient. So when we get to physics, so we know that when our gradient is positive, then our slope will increase in a way. Then when we have a negative gradient, then our graph will be descending. Same applies to the gravitational acceleration, because this is our constant in this situation, or in this case, or on this formula. Then when this gravitational acceleration is positive, when g is positive, then we will have this increasing slope, and this gravitational acceleration will only be positive if we take downwards to be positive. So when you see this when you see this graph, the increasing slope, you have to know that they took the direction downwards to be positive. Hence we'll have an increasing slope, because here on this object you can see that the only force acting on this is the gravitational acceleration, and it's acting downwards. If we take down as positive, then we will have an increasing slope. Then if we take or when we have the gravitational acceleration to be negative, that is the case where our direction, the downwards will be negative. So if downwards is negative, then it means our gravitational acceleration will be negative 9.8 meters per second squared, like this. So when you see a descending slope, then you can tell that your constant, or your gravitational acceleration, it's negative. So when you see it, the graph starting from the positive side towards the negative side, then you can see that they took downwards as negative. But when it starts from 0, or from the negative side going upwards, then you know that the downwards direction is positive. All right. So the other thing that I want us to look at is the area. Under the slope, or the area under the graph, gives us the displacement. When you talk of the area, when you get the area from the graph, if we want the area under this graph, then we will get the displacement of that particular object or that building or that mountain. So when we find the area, we know that we're gonna get as the displacement. Because for an example, if we want the area of a rectangle, we know that on the x-axis we have time, which is measured in seconds, and then here we have the velocity, which is measured in meters per second. So we want the area of a rectangle, then we're gonna have length multiplied by breadth, then which is equals to our length can be time, and then we multiply that by the velocity. Then we know that time is measured in seconds, and then we multiply that by meters per second. Then when we rewrite this, we're going to have meters per second multiplied by second. Then we know that when we multiply powers of the same base, we do what? We add the exponents. Then we're going to have m multiplied by s to the power negative 1 plus 1, which gives us m multiplied by s to the power 0. Any number to the power 0 is equals to 1. 1 multiplied by this meter, then it gives us meter. So this meter, you can see that this is the SI unit for displacement. So it means when you find the area under the graph or under the slope or under the gradient, you find the displacement. Okay, you can use the equations of motion, or sometimes you can use the area under the graph in order to find your displacement. So without a waste of time, I want us to jump straight to some questions so that we get to understand how we analyze and answer these questions. Then here we have a question. Larato throws a stone vertically into the air from the top of a cliff. The stone strikes the ground below after 3 seconds. The velocity time graph below shows the motion of the stone. Then they say we must ignore the effect of air resistance. Before we can even look at the questions, we are given this velocity time graph, which we need to analyze. So when we analyze this, we know that there is a person who Larato throws a stone vertically into the air on top of a cliff. So it means this person is on top of a cliff, and then the stone strikes the ground below after 3 seconds. So the analysis part, we know that the stone will hit the ground. So we must have a ground as a reference point, and we know that this person is on top of a cliff like this. So this person throws a stone vertically up into the air. So we have a stone here on top of this cliff, and then it is thrown vertically upward into the air. So the initial velocity of this stone, we can see it from the graph, because remember we said our formula is Vf is equals to G change in T plus the initial velocity. Then the initial velocity tells you, or it's the vertical shift of the graph. Obviously we can see that the initial velocity is not 0, but it's 10 meters per second. So it means the initial velocity of the ball here, it's 10 meters per second. Then the ball at time 1,02 second, the velocity of the ball is 0 meters. So that is where it reached the maximum height here, which is 0 meters per second at time t is equals to 1,02. Then later at the time 2.04, that is where the velocity of the ball now it's at negative 10. Then when you check the two, this is 10, this is negative 10, we talk of the time symmetry. We know that the ball, if the ball leaves the hand with a velocity of 10 meters per second, it will return to the same position with the same velocity. Then it means that the ball changed direction, and then when it reached the same position as it was before, then the velocity here was at 10 meters per second. Then at time 3 seconds, that is where the ball hits the ground at a velocity of negative 19.4. Then it means from here to the ground, the ball hit the ground at a velocity of 19.4 meters per second. Then when we check the slope of this graph, we have a descending graph. Then we can see that the gravitational acceleration here is negative. Why is it negative? Because our slope is descending. So it means our gravitational acceleration is negative 9.8 meters per second squared. It's very important to identify your constant, because it's a very crucial thing when you do calculation, because if you don't know whether your gravitational acceleration is positive or negative, then it will affect your answers, and in a bad way. So here we can see that our gravitational acceleration, or our constant, it's negative. Why? Because the slope of this function is descending. Hence we can see that they took downwards to be negative. Then we can look at the first question. It says, how long does the stone take to fall from the height of the cliff to the ground below? Remember, we know the time. It is given there on the graph, whereby from the initial point, or from path point 1 to point number 2, and then we can say this is point number 3 and this is point number 4. From point 1 to point 2, it takes 1.02 seconds. That is the time it takes for the ball to reach the maximum height. And from the maximum height to point number 3, it takes exactly the same time, which is 1.02. Why? Because this is time symmetry. And then when you multiply that by 2, the time it takes for it to go to the maximum level and then to return to the same position, it's when you multiply the time by 2. Hence, from the initial point to point number 3, it takes t must be equals to 2.04 seconds. And then from point 1 to point 4, it takes time 3 seconds for the ball to reach the ground. Remember, we know the velocity. Initially, the velocity is 10 meters per second. Then here, our velocity is equals to 0 meters per second. That is where the ball reached the maximum height. And then at point 3, where the ball reached the same height as it was before, that is where the velocity here it's negative 10 meters per second. Then when it hits the ground, the velocity now is negative 19.4. So now they want to know how long does the stone take to fall from the height of the cliff. Remember, this is the height of the cliff to the ground below. So they want the time from point 3 to point number 4. So we have to subtract the time on the last point to the previous one. So it means the time it takes, we're going to say t is equals to 3 seconds minus 2.04. And then we're going to have the difference of 0.96 seconds. So this is the time it takes for the stone to fall from this height to the ground below. Then the other question, they say, what is the maximum height that the stone reaches above the ground? So when they want the maximum height, They want the distance from the maximum height of the ball to the ground. They want the displacement from the ground to the maximum height of the ball. So we can calculate this at looking at point 2 to point 4. If we look at the ball at point 2 to point 4, we can get the maximum height there, because we know that the velocity, initial velocity, it will be at point 2. We know that the velocity of the ball, there was 0 meters per second. Then the velocity, the final velocity, which is at point 4, we know that it's negative 19.4 meters per second. Then our gravitational acceleration, remember, it's negative 9.8 meters per second squared. And then we have the time from point 2 to point 4. Remember, the ball, it took the ball from point 1 to point 4 3 seconds for it to reach the ground, and we know that it takes 1.02 seconds for it to reach point 2. So we can subtract 1.02 from 3, and then we get the time from 2 to 4, which is 1.98 seconds. Then remember, we are looking for the displacement. Then we can use different formulas. Let's start by using this one. Vf squared is equals to V initial squared plus 2 multiplied gravity change in displacement. Then our final velocity, it's negative 19.4. We square that, and then this is equals to 0 squared plus 2 into negative 9.8 change in displacement. Then our change in displacement, when we simplify this, we will have 376.36 divided by 2 into minus 9.8, and then now our change in displacement, or our maximum height, is negative 19.2 meters. So this is the displacement from the ground to the maximum height reached by the ball. Or someone can use a different formula and then say change in displacement is equals to V initial change in t plus half gravity change in time squared. Then our displacement is equals to the initial velocity, remember, it's 0. Then it means this here will go away. Then we will have half of negative 9.8. Then our time was 1.98. Then we square that. Then our change in displacement will give you negative 19.2 meters. So we get the same answer when we use different formulas. So it means this is very much correct. So our height, or the maximum height of the stone reached above the ground, it's 19.2 meters, just like that. Or you can opt for option number 3, whereby you can start by calculating the displacement from point 1 to point 2. If you calculate the displacement from point 1 to point 2, and then later you calculate the displacement from point 3 to point 4, then we'll get the same answer. So if we look at point 1 to point 2, from point 1 to point 2, the initial velocity of the ball, the V initial, there we know that is 10 meters per second. Then the ball reached the maximum height, which is 0. Then our V final will be 0 meters per second. Then it takes 1.02 seconds for it to reach the maximum height. Our gravitational acceleration is negative 9.8 meters per second squared. Remember, we are looking for the displacement, or you can write change in y or change in x. It's okay. Then we can choose a formula. I choose to go with this one. Change in y is equals to v initial change in time plus half the gravity multiplied by time squared. So our change in y will be 10 multiplied by 1.02, and then plus half of negative 9.8, and then we multiply that by 1.02, and then we square that. Then our answer now becomes 5.1 meters. So we know the distance from the top of the cliff to the maximum height. Then we have to calculate the displacement from point 3 to point number 4. So when we look at point 3 to point number 4, we know the velocity there, the initial velocity, and the final velocity. The initial velocity we know there at point 3 it's negative 10. Then we're going to have negative 10 meters per second, and then the final velocity will be negative 19.4 meters per second. And then we have our gravitational acceleration, negative 9.8. It's a constant. And then we have the time, which is 3 minus 2.04. Then it gives you 0.96. So our time is 0.96 seconds. And then we're looking for the displacement. And then now we can calculate the displacement there. We can calculate our displacement. I can choose to take this one now. Vf squared is equals to V initial squared plus 2 gravity change in displacement. Then our final velocity is negative 19.4. Square that is equals to negative 10. Then we square that, and then we add it to 2, and then we multiply that by negative 9.8, and then multiply by change in displacement. Then our change in displacement becomes negative 14.1 meters. So now we know the distance from the top of the cliff to the ground. Then we can add the 2 and get the maximum height reached by the ball. So it means the change in y maximum must be equals to 14.1 plus 5.1, 5.1. Then our answer is 19.2 meters. Then we get the same answer. So you can use as many different methods as you want, or you can opt to use the graph as well. We know that to find the displacement, because we were looking for the displacement of this graph or for that motion, we can get it from the graph by calculating the area. So when you find the area on this question, you must be very much be careful, because you can make a mistake and it will cost you. You will know how to do the maths, but the physics can be a problem, because now they want the height from the ground to the maximum height reached by the ball, which is this displacement here. From the graph, we are having this straight line. So what can guide you is they want the displacement from where the velocity was 0 until it reached 19.4. So you are going to calculate your area from where the velocity was 0. So the velocity is 0 on this line here. So where the graph cuts, that is where we're going to calculate our area. So our graph cuts, it's 0 at this point at time 1,02. So we have to calculate the area of this shaded shape here in order for us to get the correct answer. Because if we include this one from the initial point, then we're gonna have a problem. Why? Because we will be calculating the displacement minus something, because the ball, when the ball is here, it's not at its maximum, but when the ball is at point 2, which is this point here at time 1,02, that is where the ball is at maximum. So we have to calculate the area of this shape. And then when you see this shape, we can see that this is a triangle, and we know the formula for a right angle triangle. So the area, we know that the area will give you the displacement. So we can say the displacement is equal to the area of a triangle. Then our change in displacement is equals to half base multiplied by height, which is half. Then our base in this case, we're going to have 3 minus 1,02. So we're going to have 3 minus 1,02. And then what is our perpendicular height? Our height is from 0 until this point, which is negative 19.4. So it's negative 19.4, negative 19.4. Then when you punch your calculator, you will get your answer to be negative 19.206 meters. So you can see that throughout all our calculations, different methods, different formulas, we got the same displacement. So this is how you can find your displacement. You can use the graph, you can use the equations of motions, or howsoever you feel like you can bring about this displacement. There are many ways to kill a cat. So we are done with this question. Then I think we should move to the next one. Here we're given a hot air balloon which is rising vertically at a constant velocity. When the hot air balloon reaches a point A few meters above the ground, a man in the hot air balloon drops a ball which hits the ground and bounces. Ignore the effects of friction. So we're given the velocity time graph below, which represents the motion of the ball from the instant it is dropped until after it bounces for the first time. So the time interval between the bounces is ignored. Then they say that the upward direction is taken as positive. Then here is our graph. So on your far right, we have the hot air balloon here, where there is point A. We know that when the hot air balloon reached that point, the man inside this hot air balloon dropped a ball. Then when we look at this velocity time graph, we can see that the slope or the slopes of this graph are decreasing, and they already told us that the direction upward is taken as positive. Now, because we can see that this is a decreasing slope, we know that our gravitational acceleration is negative 9.8 meters per second squared. Then when we analyze the motion of the ball, I want us to analyze the motion of the ball. We are given a hot air balloon here. This is our hot air balloon, and there was a ball here which was dropped, and then it bounced on the ground, and then so we have a reference point here, which is the ground. Here we are having the ground. So this ball was dropped at a velocity, and then it hits the ground, and then it now bounces off the ground and goes up
and then it reaches maximum height, then it comes back to the ground. So I want to show you the motion of the ball on this graph. So the initial velocity where the graph starts, which is this point here, 5.88, that is the initial velocity of this ball, or this was the velocity of this hot air balloon that was moving at. So here the velocity here is 5.88 meters per second, and then it took 0.6 second for the velocity to be 0, and then now it started decelerating, it's going down. Then when the ball reaches the ground, it reaches the ground at a speed of negative 19.60, and it takes 2.6 seconds for the ball to move from the hot air balloon to the ground. So here it's the ground, for it to hit the ground. Then now there is another smaller portion of graph here. Here you notice that we took down as negative because up is positive. So here the ball bounces on the ground, then the velocity at which the ball leaves the ground, it's this velocity here, because now the motion going down is negative, 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 negative. Then when the graph goes when the ball goes up, it will be positive, 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 positive. So anything in the positive direction, anything in this positive axis, that is the motion of this ball in the upward direction. So the ball reached the ground at this velocity, and then it hits the ground. When it goes up with this velocity of 2.94. So the velocity at which the ball leaves the ground, it's 2.94 meters per second. And then now there is a point P whereby this slope intercept the time, whereby the velocity here is 0. Once it bounces off the ground, it will reach a velocity 0 at time p. So this is the point P whereby the velocity is 0, which is the maximum point. So this is the maximum where you see where it intersects, that is the maximum height above the ground. And then at time 3.2 seconds, then you see that the ball returns to its original point. So here the ball returns to the ground at the same velocity at which it left the ground. So this is the motion of this ball. This ball was dropped, it hits the ground with this velocity of 19.60, and then the velocity at which the ball leaves the ground, it's 2.94, and then it reaches a maximum height at P, and then it comes back to the ground. So they say to us, use the information on the graph to answer the following questions. Then write down the magnitude of the velocity of the hot air balloon. So this is the initial velocity of the whole motion. Then we know that that is 5.88 meters per second. So this is the velocity that they are looking for. Then the second one says calculate the height calculate the height above the ground from which the ball was dropped. So when we want to calculate this height above the ground, it means they want the displacement from this hot air balloon to the ground. So if I can try to redraw this, let me try to redraw this. So here, to find the height above the ground, it means they want the displacement from the balloon to the ground. So we can say this was the initial point, this is number 2, and then number 3 is when the ball bounces off and reach maximum level, or maybe this is number 3 when the ball leaves the ground, number 4 is when it reaches maximum level, and number 5 is when it returns to the ground. So now we're going to focus on path 1 to 2 in order for us to calculate the maximum height above the ground. Then the initial velocity there, we know the initial velocity was 5.88 meters per second, and then our final velocity, which is when the velocity at which the ball hits the ground, it's 19.60 meters per second. We have time there, which is 2.6 seconds. Our gravitational acceleration, we know that it's negative 9.8 meters per second squared. We are looking for the displacement. Then we can use Vf squared is equals to Vi squared plus 2 gravity multiplied by the displacement, 19.60 square that, which is equals to 5.88 square plus 2 into 9, negative 9.8. Change in displacement, then our change in displacement now becomes negative 17.84 meters. So this is our the height. This is the height above the ground. The height above the ground is equals to 17.84 meters. So this is the displacement from the hot air balloon to the moment the ball hit the ground. So this is how we calculate it. Or you can use the graph, because we're looking for the displacement. We can use the graph in order for us to get the displacement. So remember, this 5.88, this is the initial velocity, and then this is the final velocity, or this is the velocity at which the ball hits the ground. So actually this line here, from where it started until this point, it represents the motion from here where the ball was dropped until it touches the ground. So if you can check, we can calculate the area under this shape here, which is our triangle, and also we can find the area of this shape here, and then we would have covered the whole line, and then the area of the two triangles will result in the displacement that they are looking for. Then we can calculate that as our displacement. We know that it will be equals to the area of a triangle, but in this case it's a triangle plus another area of a triangle. Then now our displacement will be equals to half base height plus half base height, which is equals to, we're having half the base of this triangle here, it's 0.6. It's 0.6. So we're going to have 0.6, and then the height, it's from this point here to this point, which is 5.88. Then we multiply this by 5.88 plus 1/2, and then the base of this second triangle, it's 2.6 minus 0.6, which will give you 2. Then we're going to put 2 here, and then the height will be from 0 to minus 19.6, so it's negative 19.60. Then when you do maths here, your final answer will be negative 17.84 meters. So you can see this is the height above the ground. It's either you can use the area under the graph, or you can use the equations of motion. Then you will get the same answer, which is 17.84. Then for us to calculate point P, which is the time here, we can use the equations of motion, or we can use the gradient of this line. We know that here, when we draw these lines, we have a common gradient, and which is our gradient in this case. We know that it's our gravitational acceleration, which is negative 9.8. So if now we use the gradient, we have to identify the points here. If we can check this point, the coordinate of this point is 3.2 is to negative 2,94. Then when we look at point P, its coordinates for the x-axis, we have t, and then for the y coordinate, that is 0. So these are the coordinates. We know the gradient of this line, that is the gravitational acceleration, and then we have the coordinates. Then we can find the value of P, or the time at point P. So we know that when we calculate the gradient, we say that gradient is equals to change in y over change in x. But in this case, we're having change in v over change in time. Then this is equals to v final minus v initial divided by t final minus t initial. Then we have our gradient value, which is negative 9,8, which is equals to the final velocity. In this case, we're gonna put this point here, which is negative 2.94. Then we're gonna subtract this y value here of p, which is 0, then all divided by 3.2 minus point t. Then from there we can use algebra. We multiply both sides by the denominator. Therefore, we're going to have negative 9.8 into 3.2 minus t, which is equals to negative 2.94. Then from there, in order for us to remain with, or to make t the subject of the formula, you can divide both sides by negative 9.8, and then later you take this 3.2 to the other side and divide with negative. Then, or we can do it this way. When you multiply negative 9.8 by 3.2, you get 31, negative 31.36 minus 9, or positive 9.8 t, which is equals to negative 2.94. Then now 9.8 t now becomes, then when we take this one to the other side, we're going to have 28.96, and then we divide both sides by 9.8. then our time there becomes 2,955 seconds. So it means the time there at t, it's 2.99 seconds. And it's true because 2.9, it's between 2.6 and 3.2. So this is the other way that you can find the value of t at point P. Or you can use the equations of motion, whereby you have to be very, very, very careful here. when you want to use the equations of motion. So we're still gonna look at this path here. We know that at point P, that is where the ball reaches the maximum height. This is the maximum height of this ball when it bounces. And we know the initial velocity of the ball when it bounces. So this is the situation here. We know the initial ball, the velocity of the ball when it leaves the ground, which is 2.98. So if we can take path 3 and 4, we can find the value of t here. If we look at path 3 and 4, let's look at path 3 to 4. The initial velocity is the velocity at which the ball leaves the ground, which is 2.94 meters per second. And then the final velocity, we know that that is where the ball reaches maximum height, which is 0 meters per second. Then we want, okay, the gravitational acceleration there is negative 9.8 meters per second squared. Then our time is the one that we are looking for, because we want time there at point P. Then we can use this equation, the simplest equation, which says V final is equals to V initial plus gravity change in time, and then our final velocity is 0. We're going to have 0, which is equals to 2.94 minus 9.8 multiplied by change in time. And then now our time, when you solve this, our time becomes 0.3 seconds. So this time, it takes the ball 0.3 seconds for it to reach the maximum height. So we're going to add 0.3 to this 2.6 in order for us to have the exact time at P. So it means for time at P, we're going to add 2.6 to 0.3 seconds. Then we're going to have 2.9 seconds, just like this. You can see that this is the same answer that we got here. Approximately 2.9 seconds for the ball at point P. So this is how we answer that one. So let's go to the next question. It says calculate the maximum height reached, or the maximum height the ball reached after the first bounce. So they want the maximum height of the ball for the first bounce. So the ball bounces at 0.3, and then its maximum height there, it will be at 0.4. They want the displacement there. So we're going to consider from 3 to 4. The initial velocity there, we know that it's 2.94 meters per second. The final velocity there is 0 meters per second. Then our gravitational acceleration is negative 9.8 meters per second squared. Then our change in t, we just calculated it there, which is 0.3 seconds. Then we're going to have 0.3 seconds there. Remember, we are looking for what? For the maximum height, which is the displacement. Then we can use this formula here. Vf squared is equals to Vi squared plus 2 gravity change in displacement, final velocity 0, initial velocity 2.94, square that one, plus 2 minus 9.8 change in displacement. Then our change in displacement now will be equals to 0.44 meters. Even if you use the formula change in displacement is equals to Vi change in time, we'll get the same answer. So this is the maximum height reached by the ball after the first bounce. All right, so let's move to the next question. They say calculate the distance between the ball and the hot air balloon when the ball is at its maximum height after the first bounce. So this one, they want the distance between the ball and the hot air balloon when the ball is at maximum height. They want this distance here. They want the displacement from between the hot air balloon. Let me use a different color. They want the displacement here between the hot air balloon and the ball when this ball is at maximum level here. We know that the distance between, or the displacement between the ball and the ground, it's 0.44 meters. For we know the displacement here, which is 0.44 meters. And then the other thing that we know, or that we need to know, is we need to calculate the distance traveled by the balloon since the ball was dropped. All right, so the ball was dropped here at time 0, and then it took 2.6 for it to hit the ground, and then it jumped from the ground, and then until it reached maximum level there. So we know the time there, that is 2.9 seconds. So it means we need to calculate the distance traveled by the balloon for time 2.9 seconds, so that we can know how high the balloon is now at after this time. All right, this is the time of motion of this stone. So we need to calculate the distance traveled by the balloon since the ball was dropped. So the displacement here will be equals to VI changing T plus half GT squared. We know that the balloon was traveling at constant velocity. So since something has constant velocity, it means the acceleration of that object is 0, and these whatever that I've erased go away. Though now the initial velocity of this hot air balloon is the same velocity that is shown here, which is 5.88. So the velocity there is 5.88. We're going to have 5.88. Then our time, we know that is 2.9 seconds. Then we get our answer to be 17.05 meters. So this is the distance traveled by the balloon after this time. Then we have to also know that the displacement of the balloon when the ball was dropped was 17.84. So remember, we went to the distance between the ball and the hot air balloon after the first bounce, which is this one. And in the beginning, we calculated the displacement from the hot air balloon to this ground, which was 17.84 meters. Then, since we know the displacement, the initial point, the initial displacement from the balloon to the ground, and now we know the distance traveled by the balloon since the ball was dropped, then we can now have the maximum displacement for the balloon. So for the maximum displacement for the balloon, for this balloon, it means we're going to add that 17.84 plus this 17.05. So this was the distance above the ground when they threw the ball, and then this is the distance traveled by the balloon after this time 2.9 seconds. And then now the maximum displacement gives us 34.89 meters. So remember, now we are having a situation whereby now our hot air balloon, this is our balloon here, this is the ground. Now we have a situation that this is 34.89 meters, and then they wanted the maximum or the distance between the hot air balloon and the ball when the ball is at maximum height for the first bounce. So remember, the ball bounced here and reached maximum level, and we know that the maximum height for this ball was 0.44, and now the examiner wanted the displacement between the two when this ball is at maximum. So it means the height or the distance between the two now, it's equals to 34.89 we minus 0.44. Then now this is the distance that they are looking for. Then we get the difference of 34.45 meters. So this is the distance between the hot air balloon and the ball at maximum point after its first bounce. So this is it about the velocity time graph and how we answer some of the questions that might be posed to you. So if you haven't subscribed, please hit that subscribe button, like the video, share the video, and please comment on this video. Hope you've enjoyed and you've learned so much from this. From me to you, see you in the next one.